Okay, good afternoon all. I'll be talking about how Imagination Technologies uses RISC-V based processors within its GPU product IP line, and specifically we use it as a firmware processor to control and enable a lot of the advanced functionality of the GPU. So Imagination Technologies is a IP provider. As was already explained a minute ago, we've been shipped in a large number of devices. More than 11 billion of devices over the lifetime of Imagination have been shipped with our IP. Of course, as an IP company, a lot of our focus is around patent protection for the solutions that we provide to our customers. And traditionally, we are very much a GPU company where we have a lot of significant market share. So our PowerVR technology is used in more than 30% of the mobile and embedded devices that are out there. We also hold a very significant market share in the automotive space, in the SoCs with a GPU enabled within them. And we're also a key player in the connectivity space, so Bluetooth, Wi-Fi connections, and similar, and are growing in the AI market space with dedicated accelerators as well. A very technology-driven company, so more than 80% of our staff is engineers, all working on delivering that unique technology to a wide variety of customers. A very international company with both R&D and sales offices spread out throughout the world, being close to our customers, meeting their requirements, and doing local development together with those partners. Very brief update. I'm sure most people will be aware with the IP licensing model. Imagination designs the IP, the RTL, and licenses this to licensees, which typically are semiconductor companies. Although increasingly we do also see direct partnerships and licenses going to the OEMs and device makers. That can be software and support licenses, but also increasingly OEMs are fully vertically integrated and are doing chip design or are controlling the chip design themselves. So license deals being made at that level as well. Obviously, that results in silicon, which ships to consumers and generates royalties for Imagination at that point. As a GPU provider, but also as an AI provider, of course, a lot of that feedback from the consumer space, from the applications, the developers that run on those devices, that feedback and that support model there is critical for us. So you'll see references to our tool flows and how we help developers to deliver the best possible experiences to consumers. And of course, by delivering that support, we can also gain a lot of market insight that helps us improve our hardware designs, which then can continue to go through this cycle of improvement. Imagination has a number of different technologies that we provide to the market. Graphics is the core original technology. I mean, we're more than 25 years old as a business, and graphics has been the fundamental technology behind that. So within that, the key technologies are the traditional GPUs, but of course, very popular today as well is ray tracing. And we were one of the first companies to really demonstrate real-time ray tracing and hybrid rendering. So a lot of the great things we see in the new consoles, we did quite a few years ago already, and we have a very strong patent portfolio and a very efficient solution in that space. The compute side is a growing market for us. So dedicated neural network accelerators, which work together with our GPUs to deliver highly efficient heterogeneous processing architectures and unified software solutions around that, is a very strongly growing market for us. Of course, in compute, communication is very important as well. Communication between different SoCs, different boards, and solutions. And that is true both in automotive, so the central backbone in the automotive system is getting ever more complex, and we provide highly optimized and secure solutions in that space using Ethernet packet processing technology. That's also a growth space for servers and other processing types where increasingly that type of functionality is also required to, for example, scale graphics or compute performance. And as I mentioned, another branch is our connectivity solutions. So this is both RF as well as soft IP for Wi-Fi, Bluetooth, and digital radio. Overall, Imagination's focus throughout all these years has always been on efficiency. So a lot of our initial designs are very much for battery-operated devices, so power efficiency, memory footprint efficiency, execution efficiency is really key in how we approach all these three problems. So both the graphics, the compute, as well as the connectivity, power efficiency is always our first focus. The key topic, of course, of this conference is the RISC-V architecture and solutions. And for a very long time, we've been using processor technology within our graphics cores. And you can almost look at a graphics core as a small SoC on itself, right? It has a very wide ALU engine with a lot of fixed function support blocks around it. And there's very complex data flows within the GPU. And even in 1996, when we started with our GPU developments, we realized that all that complex data flow and interaction was best supported and enabled by some form of processor architecture. So from that beginning, we had a small firmware processor, a microcontroller level CPU within our GPU design to assist all the local event handling within the GPU itself. And of course, that completely offloads the host CPU. And over the years, that processor enabled more functionality. So performance monitoring of the GPU, so looking at the various performance counters, but also increasingly complex sync and control signals with other blocks. You know, that starts with the display that grew to video and camera systems. And today it's critical in terms of power management as well. So this firmware processor has generic GPIO signals that we can hook directly to a power management controller. And that means we can very rapidly respond to workload changes, adapting voltage and frequency scaling. It also enables full debugging of the GPU, right? That firmware processor plays a role in security as well, but also in understanding everything that's going on within the GPU. So step debugging, kernel dump logs. So kind of similar to a whole host CPU and an OS today, all that same functionality is possible for our GPUs. Virtualization is also increasingly important on one side for security, on the other case for robustness in, for example, automotive systems, or for enabling multiple clients in the server space. And again, having that firmware processor to watch all those different workloads, load balance them, give them priority, adapt them, a lot of those things need to be fully programmable and flexible, and a processor allows us to do that. Now, over the years, the CPU architectures that we've used have changed, but our firmware is written in standard C code. So it's actually really easy for us to upgrade and change CPU architecture. And for a lot of time, we had a proprietary CPU architecture. We've used MIPS for many years, and now we're in the process of changing that to the RISC-V architecture. So looking a little bit more in depth at all the things that firmware processor does for our GPU. As I mentioned, one of the key activities is the management of the GPU itself. So any local events that happen within the GPU, we first handle with that firmware processor. So any exceptions or any end of processing or any scheduling requirements are handled by that RISC-V processor. And that gives us maximum flexibility while offloading that host CPU. And it allows us to do a lot of priority-based schemes. So for VR headsets or for AR, real-time behavior for some of the rendering is extremely important. And using the firmware processor, we can implement very specific scheduling mechanisms to make sure that workloads are completed in time. And we can do that with the RISC-V processor within the design. The security is very critical as well. So increasingly, our automotive customers demand ASIL B level solutions, both for graphics and for compute potentially even an ASIL D level solution. And that means we can use that firmware processor for fault detection and fault handling, recovery of lockups, as well as self-testing mechanisms that we have within our solution. As I mentioned, for a lot of developers and system integrators, looking at the efficiency of the GPU is very important, and collecting information is critical to enable that. So being able to log lots of information to memory in various dynamic ways is very critical, because we don't want to have too much overhead. So performance counter processing, reporting things, crash logs, fault analysis. We basically have lots of different debug levels at the hardware level that we can basically control through that firmware processor and provide that information. And because the firmware processor is somewhat independent, even if the GPU would be stuck, the firmware processor is still active and can recover or can collect information about what is going on or where you are maybe stuck in a loop. And again, that's very critical for those security and robustness cases, the fact that that firmware processor can handle that. Often developers want to debug their applications, and the best way to do that, as we all know from processors, is step-by-step debugging and being able to look at all the registers. And the great thing is we can run a GDB server on our firmware processor, and that GDB has then been expanded to give access to all of the registers and all of the information and pipeline information of the GPU. And that means you can basically do full step debugging of shader programs of compute workloads that you are mapping onto those GPU cores. Again, that's very advanced capabilities that is supported in hardware. So we don't have to fall back to software simulations to be able to do that. We can give developers full access to what is exactly going on within the GPU system. As I mentioned, GPIO, so flexible signals to the rest of the system, gives us a lot of flexibility, because the GPU interacts with many components within the SoC. We typically interact, of course, with the display, so sending images to the display is the most common for a graphics processor, but very central in the system, that's the output part. There's a lot of different inputs into the GPU as well. So direct communication and direct interaction with, for example, a camera interface, or with video decoders, or for a cloud gaming solution, synchronizing with very low latency to a video encoder so that the game images that the GPU generates can very quickly be encoded and sent to the client. All of those things become extremely efficient if you can send direct hardware sync signals rather than having to throw an interrupt, go through a lot of software on the host CPU, and then send that information on. So all of that is very flexible and programmable, which means that we as an IP supplier can adapt to a lot of different system environments. DVFS power management is very critical in a lot of our markets. And of course, you can imagine there that power in a mobile phone is absolutely critical. And the best way to achieve low power is the lowest possible voltage and frequency. So being able to look at the workload within the GPU and basically tuning that frequency and that voltage as required by the workloads that we see allows us to get the lowest possible power. So we can look at how busy the GPU is. We can look at the timelines to make sure that we can hit 60 FPS or 120 FPS for virtual reality headsets. And we can detect if we are running behind on that deadline. And that really allows us to have very flexible and very good user experience while keeping the power consumption of the GPU as low as possible. And all those complex activities is what is possible by that firmware processor. And because it's fully C programmed, it's very easy to read, very easy to manage, and even to deal with by our customers. As I mentioned, developer support is very critical, supporting advanced tool flows. And again, a lot of that is made possible by that RISC-V processor within our GPU. So on the left, you can see an illustration of our hardware performance profiling tool. And actually, you can see all the different workloads, but not just for the GPU. It goes all the way back to the driver and the host CPU. So we can track and tag all the different events and workloads, and we can see them going from the host CPU through the driver, through the scheduling mechanisms, to actual execution on the platform. And all of that advanced management and information we can get back thanks to that RISC-V processor. As I mentioned, full debugging of the GPUs, full source level debugging is made possible by running that GDB server on the RISC-V processor and then connecting to it from a host platform. And then we can see the full code, we can see all the different low-level registers, but equally you can do full visual source level debugging at that point as well. And again, fully supported by the hardware. And this works all on Android phones. So that gives you an idea of the very capabilities that we have. A little bit of detail. It's like I said, we use a small firmware processor, a microcontroller level solution. And we embraced this very quickly, and we started from the Western Digital Swerve implementation. But of course, as we are a full IP supplier who operates in the automotive market, a lot of our work was on the validation, verification, documentation side, as well as fully integrating this with our GPU infrastructure. So that's where a lot of our tuning has focused. Adding better data cache support for good performance has been very critical for us there as well. And as I mentioned, a baseline for a lot of the functional safety requirements is a form of ECC or EDC protection. So this was also added to the system. Compared to the previous kind of micro MIPS implementation that we had within the system, the great thing is that this processor is giving us 40% higher performance as well. So lots of benefits for us, because obviously we're benefiting from a very modern, very dynamic, very widely supported CPU architecture, which can build on a lot of the tool efforts that everybody in the community is making. And additionally, we've managed to tune this very specific to our usage case. Of course, as I mentioned, good hardware is not worth that much unless you have all the software and all the tool flow that goes with it. We know that very well from our GPUs, and of course, this is true internally as well for supporting that firmware. So making sure that we have our own SDK supporting that CPU engine, so the latest versions of GCC and LLVM compilers, and specifically tuning that for our implementation of the Swerve processor. Optimizing some of the very small, highly optimized libraries that we use as well as a key activity there as well. And again, we've inserted that into our own software development environments as well. Again, full GDB support, simulator support, all of those things have been done. And we're very agnostic in terms of the development tools. So support for Linux, Windows, and Mac OS is pretty standard for us as a company. So again, making sure that our internal developers can fully take advantage of that RISC-V architecture to deliver the best possible GPU experience. So what does that enable in our GPU market space? We have 4 different families now of GPU solutions. The BXE series, our XE series, is our entry-level solution. So this targets UI-centric applications, so consumer market. Is very widely used by our DTV and set-top box customers, but also increasingly industrial customers. And this means very low cost, very small, 1 square millimeter designs to enable very efficient display and user interface processing. Our XM range is more of a mid-range solution, so increased compute capabilities on the GPU side, and this transitions you into the kind of entry-level, low to mid mobile phone markets. Our BXT series is the high-end. So that targets, high-end premium mobile phones and everything beyond that. And that will become clear on the following slides, where you see our approach to multi-core which allows us to go from mobile, ultra efficient, very power efficient, very high performance efficiency devices and scale that into server and PC markets as well. And then the BXS, the S for safety, this is where we can take any of the previous families, so from the very small consumer cores to the very high-end server level solutions, but we can make them specifically functionally safe, so enabling them for the high-end automotive markets, but just as well the entry-level automotive markets. So XT, a brief look at that scaling from premium mobile all the way to the cloud. So we've moved to a very decentralized approach for our multi-core scalability. And again, a lot of that is made possible by that RISC-V based firmware processor. And what you can see here is that we can instantiate many of these large GPU instances, and they can be distributed over multiple chiplets. But our approach to workload distribution, which is made possible by that firmware, allows us to deal with these differences in latency, and it avoids having a single central dependency. And we can make all of these work together or treat them as independent. And that gives you a lot of flexibility for security, for robustness, for functional safety, as well as virtualization. We could split off a GPU and give it to specific tasks. But as the next slide shows, we can bundle all of them together and turn them into a really large GPU. And these firmware processors then work together to make sure that workloads are completed in the most efficient way possible. Of course, as I mentioned, we can take those variations, we can make them automotive, so we tune them specifically for the automotive workloads, where we can offer up to 60% higher performance by doing that. And we then support a lot of integrated safety mechanisms at the graphics level, so tile region protection, being able to flag specific elements in the UI in your dashboard as functionally safe, and then applying redundancy and verification dynamically to that. And that avoids the cost and the overhead of full lockstep solutions. And of course, by having natural redundancy in that, we can make a lot of verification steps very easy. But equally, because we have two cores, there is a whole variety of different types of hardware virtualization that we can support. And just to show you, one of our customers for this already is in the autonomy space, so self-driving cars. And this is actually where multiple of our IP blocks can come together. So at the top, you can see our high-end GPUs, so the multiple ALU processing clusters of the GPU, the support logic, but then centralize the caches and the control logic with the firmware processors. So this is our floating point number crunching engine for the ADAS algorithms. But again, as I mentioned, that firmware gives us a lot of flexibility for operating with other blocks in the system. And down below, you see one of our other IP lines, our neural network accelerators. So the highly optimized inference solutions, which are working on fixed point data. So again, a massive multi-core array of those and very efficient mechanisms to work together through these on-chip memories. And again, these firmware processors within these IPs can coordinate, can synchronize, and can deliver the highest throughput and efficiency in data flow. Our solutions, as a result, are extremely scalable. You can see that there's lots of different performance points and efficiency levels, and equally silicon area and power budget points that we can enable from our product line. That's really the top level overview that we wanted to present here to you today. Thank you.
Thank you for presentation. So I checked the questions from the audience. So I could not find. So I have a question. So about can I ask? So
sure.
Yeah. So I think so GPU. Yes. The question is about GPU based on RISC-V architecture. So I think changing architecture is not so easy. And I imagine GPU ISA instruction set architecture is different from RISC-V. So are there some special approach or just instruction decoder is changed, or how to do the change or treat the RISC-V ISA?
Right. So it's not an approach that we've taken. We know that there are some GPUs out there who are trying to replace the GPU ALU units themselves with a RISC-V solution. Kind of turning an array of CPUs into a GPU is something that's been tried many times before, but unfortunately has always failed. So Intel very famously tried this first, but the real benefit of GPUs comes from the fact that it is not a CPU. So the way the ALU pipelines work, the way they do their processing is vastly different from what a CPU is optimized for, right? A CPU is very optimized for single-threaded behavior, for very dependency on a large cache, and a GPU is much more a very parallel data streaming solution that depends a lot on fixed function blocks that sit around it. A standard instruction set does not exist for GPUs, right? If you look between different vendors, we all have different ISAs, and the APIs also don't give you any benefit from having a shared ISA because they all operate at a source level. They all expect an on-the-fly encoder. So there's no such thing as binary compatibility in GPUs. And that's a good thing because it gives us massive flexibility to very quickly adapt to market needs and changes. And GPU ALUs over the years have changed a lot. So it's not one of the things that we've been trying to do. And from a power efficiency point of view, it would also not be a good direction to move in. Where the RISC-V really does give us a lot of benefits is as that firmware processor. So the top level control, the flexible scheduling engine, and that is effectively where we are using the architecture. So the management of all the work that's executing on the GPU. So on a lot of GPUs, that is state machines or something that's very fixed function, but that is too limiting because workloads on GPUs are becoming too complex and too diverse. And we recognize that very early on, as I showed in our timeline. And having that firmware processor there is very effective for our customers. And because increasingly people want to play with that scheduling, having a C-based firmware, a standard architecture at that level is very beneficial for the market.
So then the firmware architecture, firmware controller is based on RISC-V. Is that right?
Yes, that's correct.
Okay, so then your GPU has, each GPU has a firmware controller and its good benefit of RISC-V and maybe software in the future. So, okay, yeah. Thank you so much for answering. So
my pleasure.
Yeah, thank you so much. So now, one question here. Yes, question to you from audience. Did you introduce any special instructions to the CPU? Yeah, so maybe adding instructions was.
We've not specifically changed the instruction set of the RISC processor. The only thing that we've changed is some of the register interfacing. So the biggest changes is in the exchange of information with the GPU. So some of the control registers, etc., are being given access directly by that firmware processor. So it's mostly an integration change, not an instruction set change. So we can use a lot of the standard tool flows.
Thank you. So, and another question from audience. How can you achieve the safety with low-cost lockstep? how can you achieve the
So
safety with low cost lockstep? Yeah.
yes. So the traditional approach to safety, of course, is to run everything twice and to lockstep them. If you look at GPUs and graphics usage case, what we found was that cost was too high. Most of our customers said we cannot put twice the GPU in to get safety. And if you look at the rules for especially graphics rendering, not that many things on the screen are functionally safe. So a lot of is information, and that information is not critical. And functional safety is very much about ensuring that the critical information reaches you. So, for example, warning lights can be critical. So, for example, if your brakes fail or if your engine has a problem, that's a critical information because it can impact the safety of the car. But a lot of the other information, if your map disappears or if even your speedometer disappears, that's not critical information because you can still look out of the window and see what's going on. So what we can do is we can tag different objects as we are rendering, saying this is absolutely critical. And that means we only verify those elements on the screen. And what that means is you maybe only 5% of what you are rendering is actually functionally safe. And then you put your lockstep effort, your replication effort on that. Again, we then have lots of different redundancy mechanisms within the GPU, so being able to switch ALU pipelines. So even if you execute them over time, we can send calculations down different ALU lines within the GPU so that we have, abilities to detect if any of those elements has been broken or is impacted in its functionality. For compute, it's kind of similar. With compute, we find that a lot of customers have different ways of getting redundancy and robustness. You don't necessarily have to trust each execution. So one of the ways is to run one algorithm on the GPU, run another algorithm on a different GPU, and compare them. So you can get different ways of covering, because ultimately they use a voting mechanism to achieve functional safety. So they might run neural networks or classic vision to recognize pedestrians on the GPU, on another GPU, on a neural network engine. And then they have a three-way voting system to get safety across those different cores. So there's lots of different levels of testing that are needed. How quickly do you detect faults? So by dynamically being able to toggle verification and validation and replicating work, we can basically tune from an ASIL A level, which is low level of verification, all the way to an ASIL D level. And ASIL D means you're doing lockstep because it's near 100% coverage that you need to have. So we've basically made a lot of the lockstep mechanism fully dynamic in nature. So we can basically tune the percentage, if you want, of validation that we do for the workloads.
Thank you for answering. So just I think one other, this is just question to you, I think. The question is, I think GPUs are strong on dense data, but weak on sparsity data. Is there any way to solve this? Yeah, please.
Indeed, GPUs are inherently parallel processing architectures, and that's their strength. And this is why we very much see that trend towards heterogeneous processing. And this is why the collaboration of the GPU with CPUs, with neural network engines becomes very critical. So because if you start to make the GPU ever better at sparse data, at some point it becomes a CPU or it becomes a neural network engine. And that's going to be the real strength of heterogeneous solutions going forward. And again, this is where these firmwares become very critical, because we want to be able to run, very parallel, very coherent data, if you want, through the GPU. And then if we have very branchy or very serialized atomic access style parts of algorithms, we kind of want to say, well, the GPU is not good at that. It's not optimized. So can we give it to maybe an array of CPU engines to execute more efficiently? Or do we give it to a neural network engine which can deal with the sparsity of having, the zero pruning kind of concepts that we see within neural networks. So there's a very interesting balance in terms of how much you put in the GPU and how much tuning you do, because the GPU is not the universal processing solution. So you have to kind of find the right balance between what you optimize on the GPU and where you say we want to move this to an other processing resource within the system. And especially in mobile phones, that's already the case today. Mobile phones, where we see most of our customers, they have big variety of CPUs, very big NNA engines these days, and a large GPU. So that heterogeneous flexibility that the firmware gives us, so very synchronization flexibility, is one of our key strengths.
Thank you. Thank you. That's all question to you. So thank you so much for a very good and effective presentation, and I think I understand very much you. So just to finish, can I go to our next session?
Thank you.
Yeah, thank you.
Right.
Thank you. Yeah. All right, thank you. Okay.